Hello, can you hear me okay? All right, well, let me start. The organizers for the kind invitation to speak today is really, it's my first time in India and I'm enjoying being here a lot, looking forward for more discussions as well. So yes, so I'm giving 4 lectures or 4 talks this time. So this is the first one that I will start. This is the first one on quantum simulation. I choose it to try to have a little bit more connections with quantum simulation. And I'm going to tell you about quantum chaos and entanglement in trapped ion crystals. So please feel free to interrupt me whenever you want. Please, I like questions. All right, so before I start, I want to emphasize that this work is a very close collaboration with John Bollinger, Trapped Ion Group at NISER. We have been collaborating for many years and has been very exciting. And now Alison Carter is the one who he's retiring and she's taking the lead. And of course, fantastic grad students and postdocs taking the data. And my theory group, many of them actually have graduated and now or are postdocs and even have faculty positions. And I want to emphasize the work done by Chan Mulade. He's a postdoc now at JTI. And of course, many fantastic collaborators. All right, so I always want to start by sharing my vision. And I hope that we all find as exciting as I do. So what we want to do is harness quantum complexity. Basically, we want to understand how many body quantum systems behave and use them for applications ranging from quantum simulation, quantum information, and metrology. And well, so I think my goal or the goal that we want. Not working, okay. Is that better? Okay, great. Okay, yeah, so what we want to do is trying to bridge the complicated gap between the behavior of few body systems to the exciting properties of many body systems. And for that, we believe that AMO systems are very exciting and offer great opportunities because they have very well understood microscopics. We can tune the interactions even on real time, and we can have access to quantum dynamics many times, for example, without the need of ultra-fast tools. So in my view, these systems, and they include atoms, molecules, ions, offer fantastic opportunities for the fall for what I believe very exciting goals that we want to achieve. So we wanted to be able to create new type of advanced materials that's in the topics of quantum simulation that we can understand what happens in solid state systems and then even make them in conditions that are simpler and help us to understand the underlying physics. Of course, we wanted to generate or create a quantum computer and allow us to do many calculations that we cannot do with classical computers. And of course, atomic systems have been a holy grail or very useful for metrology or quantum sensing, and we wanted to push them from systems that sense using classical states towards taking advantage of their entanglement for better sensing opportunities. And with these better sensing opportunities, we hope that we can use them for understanding key questions in our universe, like dark matter, dark energy, many open questions, connections with gravity. So in this talk, I want to try to show you how we are trying to address a connection, especially through these 3 directions. And for that, I'm going to explicitly mention atomic clocks, because these atomic clocks are a clear example of how over the years, atomic systems are pushing the frontier and improving the sensitivity almost 1 decade every year. The progress is super impressive, and we are now reaching a sensitivity that is the order of 10 to the minus 19. This is the most accurate clock. Actually, is now a single ion aluminum clock. That's what reached is only 1, so it's mostly accurate, so, but still very impressive progress. But that means that when you think about that, still we are using atoms in a way that we are limited by their classical, but the classical properties, in the sense that independent atoms are still very noisy, and they are fundamentally limited by the standard quantum limit on the sensitivity that we can get with them. And what we want to do is actually really break this wall that limits the sensitivity in classical systems, and try to push them via entanglement to reduce the internal noise of the atoms, and reach what is called the Heisenberg limit, that is the fundamental bound when you have entangled particles. So this is super exciting, and this has been the efforts over many years, and will continue. Let me say, nevertheless, that regardless all the efforts, currently all the state-of-the-art atomic clocks are operating at the standard quantum limit. So this is the direction that we want to push. Why it has been so challenging? Well, because in the context of entanglement generation, we have to overcome the coherence. We have to make the entanglement generation process super fast, because otherwise we are going to be the entanglement, the fragile entanglement that we generate is going to be correct. And one caveat is that typical interactions that happen in neutral atoms are short range in nature. They are contact interactions, and therefore there are limited by fundamental bounds on entanglement propagation speeds. Like this domino, one has to fall next to each other, and these are the called Lieb-Robinson bounds. On the other hand, we can think of all-to-all interactions like baseball players, so in which the intermediate of the interactions are phonons or photons. Then the atoms, no matter where they are in the array, can interact with its partner, and therefore we can actually remove this, the constraint of this Lieb-Robinson bound, and have connections of more infinite range interactions. So among these systems, atoms in optical cavities and trap ions are ones that are pushing or are enable us to actually reach this type of set of interactions. And today I'm going to focus mostly on trap. So let me start discussing the experiment that we are working. This is the NISER trap ion experiment that uses beryllium. In beryllium, we form 2D crystals that form at triangular lattices. These are actually an experimental image of the ions. How this is done is we subject and we trap the ions in what is called a penning trap. That is a cylindrical stack of electrodes that provide the axial confinement. And in order to provide the radial confinement, what we do is that we rotate the ions in the presence of a super strong magnetic field generated by superconducting magnet of the order of 4.5 Tesla. And with the strong magnetic field and the rotation, because the ions are charged, they start to feel Lorentz force that provides the radial trapping. These are some numbers, just for interest. 1.5 is the axial confinement and 100 kilohertz rotations. So in this case, then the ions are assembled because of the column interactions into these 2D crystals of that are shown here. We choose two internal levels of the ions, one that has electronic spin, although in general, you can also, in principle, take advantage of the nuclear spin, but at the moment, we are going to isolate just these two levels, internal levels, that are separated by of the order of 100 gigahertz. So because of this separation, we can, energy splitting, we can use microwaves in order to drive single qubit transition in the system that with very high fidelity. Some disclaimer or some exciting note is that for many years, the penning trap group at least was the only group doing many body physics. And in the last couple of years, there is a slew of new type of platforms that are starting to explore this type of the crystals in Georgia Tech, in Sydney, in ETH, and not only in penny traps, but also even ball traps, exploring to the ions in crystals, for example, in China, in Innsbruck. So it's very exciting that there is a lot of new developments towards this direction. Okay, so the ions in the crystals are not so close to feel spin-dependent column interactions. So we have to induce them by light, and this is done by illuminating the ions with a set of Raman beams with a different frequency mu that you can see as generating a moving lattice because of the different frequency. And what we do is that we choose the frequency and the orientation and the polarization of these Raman beams such that they introduce a spin-dependent force. So a spin up moves in different directions, in opposite direction that is spin down. So this is what I write here. This is the force. You can see sigma c is the Pauli matrices. It changes sign. We go up and down, and we control the strength of this spin-dependent force by this equal frequency mu, because we want to tune it to specifically select what type of motion we want to excite. More explicitly, because the ions are interacting via strong column interactions, they cannot move independently, but instead they move to a set of drumhead modes. And what we do is that we're going to choose the big node frequency to actually select the type of mode that we want to excite. This is a picture of the modes. It's just a cartoon, but you want to see them. The highest frequency is the center of mass mode. And this is when all ions moving together. And this is the one that we wanted to actually excite. So we're going to put our mid-node frequency very close to the center of mass. So we ignore any other modes in the ions. They are oppressive, so they don't participate. And in that case, the Hamiltonian reduces there a lot. So now we only have the center of mass mode that is created or destroyed by this full operator A that talks with all the ions together because they are all doing the same at the center of mass degree of freedom. Therefore, we instead of single SC, we have the collective spin SC that is the sum over all the spins of the ions. And the square root of n here is because all the ions are moving in sync, and therefore the mass increases by n. That's it. So this is the Hamiltonian that we have. In the past, we were interested in trying to see how we entangle the ions. And for that, we thought, well, maybe we operate in the regime where the phonons are just intermediators. They just mediate the forces of the interactions. And in the regime for the tuning, that is the difference between the bit node frequency and the center of mass mode, is maybe very large compared to the coupling frequency. Then the phonons are really hard to, high in energy. We cannot populate them, and therefore we just can adiabatically eliminate them and do second order perturbation theory. And in this case, after the phonons are enslaved to the spins, and we have what we call one axis twisting Hamiltonian, that is a collective interaction where all the that is have been known to be very iconic for spin squeezing. So spin squeezing because, or entanglement, useful for metrology, because if you look at if you prepare the collective spin, for example, pointing along the x direction, along the perpendicular directions, this acts as a magnetic field that shears the distribution in opposite sign if you are close to the north or the south pole. So this shears the distribution generated what is called one-axis twisting that is producing the noise along one direction, and this is useful for metrology. We tried to do that a few years ago. I don't want to go into much details, but what I just wanted to say is that we were able to prepare states with about 4 degrees of spin squeezing in a system of 86 ions, which is okay, but not so good. And the limitation when we were trying to increase the ion number and we didn't improve in the squeezing is because light scattering was a problem. So the reason is because when we adiabatically eliminate the phonons, then the speed is reduced by the larger the tuning that we have, and slow down the dynamics compared to the bad processes. So what we want to do now is to go faster instead of further tune operate at the regime where the phonons are resonant properly and try to speed up the rate at which generate entanglement, the fastest that we can. This, the fact that we keep the phonons alive is what gives rise to generate in the ions what is called the Dicke model. So in our system, we just need to add an additional transfer field, and now we're going to keep the phonons alive. So the Dicke model actually is an iconic model in quantum optics that was proposed since the 50s and has gained renewed attention in ultra-cold atoms experiments. And in fact, there have been beautiful experiments trying to explore phases of the Dicke model in optical cavities. And for example, not only started in 2010, but actually experiments keep progressing and exploring the Dicke model. There's very nice experiments in tweezers now with full control. But something that it's important to emphasize is that in cavities, the photons leak out of the cavity. And therefore, when you explore the steady state phases, the cavity decay always plays a role. In contrast, in the phonons in the ions, they don't decay. They are super stable. And therefore, we can genuinely explore the unitary dynamics of this model. So that's what I'm going to tell you. We have the phonons, the transfer field, and we're going to explore the role of spin phonon coupling in the systems, giving rise to the full power of the Dicke model. A few years ago, we actually showed that in fact we implement the pristine model in the ions, but now let's try to explore the entanglement properties. So this is going to tell you about today. This is a recent work that we have in the archives. But I mean, I just wanted to emphasize that the Dicke model has been known because it has very rich behaviors from chaos, scrambling, entanglement generation, and this has not been seen yet. So that's what we are trying to do, trying to explore all of these in this set. Okay, so we are going to explore dynamics of the Dicke model. So we want to explore what is called dynamical phases. That means we're going to do some wedges. So this is the phase diagram. This is theory calculations of the phase diagram of the Dicke model when we start with all ions pointing down and the phonons in the back. This is what happens with, and then we look at the evolutions of the average magnetization SC. This is the quantity that is plotted as a function of different parameters. That is the ratio between the Rabi frequency and the tuning. These are the kind of the single atom, single ion parameter, single phonon parameters, and the ratio between the Rabi frequency and high is the effective interaction. I'm going to explain a little bit more. This is just to show that if you look at this phase diagram and the one that you get from a mean calculation, where we ignore all the type of correlations, this is done actually exact diagonalization because it's to diagonalize. You can see that they agree. No, I'm going to explain the details. So now the experiment has also the possibility to tune the initial temperature of the phonons. It can start very close to the ground state in bar equal to 0.5, not 0, but 0.5. And we also can make the phonons not so cold around in bar 5, and we can change the number of ions depending on the initial conditions. Okay, so let me start to explain a little bit the phase diagram. And at the beginning, we wanted to make sure that we reproduce what was done before in the regime where delta is large, so the phonons can be adiabatically eliminated. So this is going to be this exploration here, and then I'm going to explain a little bit more toward the chaotic regime. So let's start here in the regime where we are going to be able to adiabatically eliminate the phonons as before. Delta large compared to any other energy scale will recover the one-axis twisting Hamiltonian plus an additional transfer field. This is called the LMG model. This model has been explored for many years, even in also recently in cavity systems. We explored them at GILA as well. And well, we can also think of the other extreme regime where what is adiabatically eliminating is the spins. So in this case, instead of the spins playing a role, the quadrature of the phonons play a role. I'm just saying that there can be equal type of of behavior. I'm not going to focus too much on that. But in general, for these two cases, what I wanted to explain is that there is we can choose the order parameter, for example, the SC for this case, of the position of the phonons for this other case, and we can write multiple equation of motion, and this gives rid to kind of Newton equation describing a particle moving in a potential. So what happens is that this simple treatment, the particle can be in a potential where the energy of the particle is much higher than any barrier, and the particle can move all the way that we call entrapped. Or you consider the potential because of the interactions of the system can be large, and then therefore the particle can be trapped without moving on, only exploring a small region in phase space. Well, this is exactly what we see when we start in the regime where the interactions at large remain high, is what determines the interactions. When the interactions versus the radio frequency are large, so this parameter is small, we see the phonon, the magnetization being almost not evolving if you start along the south pole. But as we increase the ratio, actually the spins start to be able to rotate more, so you can see that there is more exploration. And then as we make the radio frequency larger, you can start to have almost full rotations, all the way when you have almost just a simple radio flopping of the system. And in fact, if you look at the time average of the magnetization, that is what was plotted in the phase diagram, we can see in fact that there is a transition where the system doesn't evolve too much. And then when the aeroid magnetization goes to zero because it's just rapid flow. Just mentioned that the solid lines are full numerical calculations, including all the sources of the coherence that agree very well with the experiment. And the dashed pink lines are going to be meeting calculations, and you can see everything agrees super well. Moreover, the blue and the orange, that are the different temperature of the phonons, overlap completely, explaining why the phonons are adiabatically eliminated and not take any role. So it's just as you expect. Now the dashed black line that is supercharged is when if in the ideal case where we can wait for a very long time. This is not the case in the experiment. So the experiment is not so sharp because we have to do the time average of the finite time window. But it's not because of the finite number of particles. It's just the time. Okay, but we see the phase diagram between the trap and the trap phases. But now let me focus on the direction. And for that, let me remind you that we want to characterize chaos in a classical system. What we do is that we write phase space variables. These are the spin orientation and the position and momentum. We write what is the evolution of these variables in phase space and how they differ by a small change in initial conditions. And if they differ a lot, it's characterized by the Lyapunov exponent, that is an exponential divergence of the trajectories for very small changes in the initial conditions. So we can compute the Lyapunov exponent. And, this is the theory, and you can see that the regions for the Lyapunov exponents are super large, and this is the chaos in the Dicke model. So what we wanted to do is try to store experimentally this chaotic regime. And well, this is the average of the magnetization versus the ratio omega divided by delta as we go across this path. And we are going to see this point in the square where we are going to still in the region where chaos is not relevant. So this, then we're going to be the region where chaos is important here. And then the region where chaos is not relevant and the phonons can be instead adiabatically eliminated. So now this is the change of behavior of expectation value of the C. I'm not showing, I know this doesn't show the chaos specifically. I just wanted to show that here we see a lot more deviation with respect to the mean view, and that still there is not so much difference in the average from the deviation between the red, the orange, and the blue points. But if you look at the theory, on the other hand, if you look at the number of phonons, we see that the phonons start to become most populated in the what we think is the chaos region. So let's try to think about the quantum measures and if we can really see some signatures of chaos. So for the signatures of chaos, let's try to look at the expectation value of SC versus time, experimental observation in the region where we are almost in the region where the phonons can be adiabatically eliminated. we start to see, and this is the experimental data, this is a parametric probe of SY versus SC, and you can see that the trajectories are not so regular. But when we go to the chaotic region here, you can see that the trajectories are really very non-regular. There are kind to see some type of chaotic behavior. This experiment will start to get significant from the experimental solution, the experimental data. The blue and the cold and the hot phases start to differentiate significantly. And then we can see that as we go to the other region that is no longer chaotic anymore, you can discover these very nice smooth orbits that are just regular trajectories. Mean field still deviates a little bit, and then you go back to fully regular orbits restored in the field. So there is some signature of chaos. We see that there is some deviation between mean field and the exact and the ideal theory and the experiment, but I have not shown you any simulations of entanglement yet. So for that, let's start exploring the other conditions where we start in a point where there is no mean field dynamics at all. So let's start in a situation where, imagine the photons are very cold or ideally in vacuum, and when we start pointing along the x direction. In that case, the strings are in an ideal state of the system, and the photons are in vacuum, and so the expectation value of these two quantities, expectation value of A, expectation value of C, are both zero, so that the mean field, if you look at what is the dynamic, is zero. But if you start solving that, including both quantum and thermal fluctuations, in this case, all the quantum fluctuations, you see that there is dynamic. And this is the regime that we're going to explore experimentally. So let me first start explaining why we wanted to focus in the regime where omega and delta are equal. So this is the regime, the code that we're going to explore. The reason is because if we're going to explore the regime where omega and delta not only first are equal, but are large, we can go to the rotating rate of the non-interacting Hamiltonian. And what happens in this case is that these operators acquire just space. So I'm going to write SC in terms of creation and destruction operators along the x direction. So you can also rotate and think the other way around. But you can see that in this case, they just get spaces that are proportional to omega, and the A it spaces proportional to delta. And the important point is that if delta is much larger, equal to omega is much larger than G, there's only one term that is survived. But it's the case when you are creating a phonon and creating an spin expression. And this is a pair production process where a phonon and spin expressions are correlated by generated in pairs in a correlated manner. So basically, we start with no spin excitation and the phonons in vacuum. As a function of time, you can see one spin flip and one phonon excitation, two spin flip, two phonon excitations. These, moreover, are created fast because exponentially fast because there is no barrier. You just create them at no energy cost. There is an exponential growth of these correlations, and furthermore, this is a characteristic to more the squeezing process where you have a squeezing along the hybrid quadratures between the phonons and the spins. So there is a P quadrature and a C and a Q quadrature and a Y. And you can see these two quadratures are independent. And moreover, along one direction, you have a squeezing and the other direction are anti-squeeze. And this happens in a very fast rate exponential. So let's see if we can see that in the experiment. So indeed, these are experimental traces. I'm going to go into these 2 points. The point here where delta and omega are large, and the point here where actually the counter-rotating terms that I neglected cannot be neglected. So first you see that in fact you have an exponential growth. This is the green phase, and the exact solution, the theoretical solution for include all quantum effects agree very well with the experiment. There is exponential growth here, but in one thing you have oscillations. These are actually collective quantum gravity splitting oscillations. They are completely quantum. They are not mean fields. They are not single particle rotations. And you can see that the mean field theory is completely off. And furthermore, if you see on the other hand in this regime where the counter-rotating terms are important, instead of oscillating, you see that you have the expectation value reaches a 0. So it flattens out. Mean field is also super bad. And here what we wanted to explain is that the only way that we can make mean field agree with the what is observed in the experiment is we add by hand in the theory certain amount of initial temperature on the phonons, but we need to add more than about 5 times what we have in the experiment in order to make theory and experiment agree. So that means that the dynamics is fully quantum. But let's explore a little bit more that part. And let's see about if we can have some indication of income. So if you think about a closed system, the Rayleigh entropy is one of the measurements of weakness of entanglement. Rayleigh entropy is to trace some part of the system, this A, and then you look at the purity of the reduced density matrix of the system. For the case when you have a collective system and where we guarantee, this is what we mentioned in the experiment, the expectation value of Sx and Xy0, the Rayleigh entropy of a single string, the most simple type of Rayleigh entropy, can be characterized and connected one-to-one to the expectation value of Sx. So that means that if we are going to look at there is one-to-one connection between these two, and this is what we see. I mean, now Rayleigh entropy is not a good characterization of entanglement for an open system. So we have to be very careful. So what we do is that we plot the Rayleigh entropy for the ideal case, no sources of decoherence at all, and we compare it with the theory where we include decoherence as with experimental data. And we see that while in the chaotic case, where there is no oscillations at all, the system saturates and reaches the maximum Rayleigh entropy possible for one spin, we see that the ideal system and the theory agree very well, supporting that we have entanglement living in the system. In the other case, we see that the theory, ideal theory, behaves different from the experiment, so we cannot use the Rayleigh entropy as a value, as a trusted quantity. So in this case, we can only trust the Rayleigh entropy that reaches its maximum value at all. But nevertheless, we can look at the quadratures of the corresponding components, and we can see that this is the minimum, I mean, this is the variance of this hybrid component as a function of omega divided by chi. And we can see that in the ideal case, it reaches a value below the vacuum noise. That means we start to see there is entanglement. And if you start to include all the sources of decoherence, it's not as large. But if we plot at this point, at this value of omega divided by chi, at this point, we plot the dynamics of this quadrature, the minimal quadrature versus time. We see that while the DR is going to reach 8.3, we are going to see in the including noises, source of noise, 2.6 degrees below the vacuum noise, and actually around 4.6 degrees below the permanent noise. So we are starting to see signatures of entanglement even in this case. So how is this going to help us with metrology? So in a prior experiment in John's lab, we were using this Dicke model in the absence of the transverse field in order to perform measurements of electric field. And we were able to entangle the spin and the phonons, and actually we were able to report a sensor of electric fields, AC electric fields at about hundreds of megahertz frequencies that are with a sensitivity of 240 flat minus 10 nanovolts, maybe per meter per second. Maybe this doesn't mean anything to you, but it's a kind of the state of the art. But we had problems with the center of mass fluctuations. So we feel that now by taking a full exploration of fully account of the Dicke model and make the dynamics exponentially fast, we should be able to improve that. Why is this exciting? Because in the ion there is a very strong magnetic field, and therefore in the presence of a strong magnetic field, there are actions in the form of dark matter manifest as actions. There is a conversion between the electromagnetic field to actions, and therefore we should be able to be sensing actions at very interesting frequencies. So we believe that with this type of improvement, in fact, this type of data model could be useful for applications in metrology. And I think that I'm starting reaching out of time. I just wanted to say that, I mean, I didn't mention about the scrambling. I mentioned about chaos, a little bit about entanglement. I didn't talk about the scrambling. But of course, one of the holy grails, the connection between thermalization in the system and the fact that the system is scrambling quantum information. Okay, one second, it's going to be super fast. I'm not going to go through this, just going to that as the system thermalizes and the Rayleigh entropy of a subsystem, which is becomes non-zero, then what happens is that the system is becoming entangled, and or that there is a scrambling of the quantum information that is distributed across all the many body degrees of freedom of the system, and therefore, because the system thermalizes, then people, I mean, in high energy, they wanted to start making connections between the scrambling and the solution of black hole information paradox, because information is not destroyed, but distributed into the many degrees of freedom. So I will not be able to tell you the story, just highlighting that it's believed that nevertheless in black holes, this information could be recovered from the Hawking radiation by looking at a little bit of a part of the Hawking radiation and doing an appropriate unitary piece that will do the scrambling of the black hole. We should be able to recover that type of information. And there have been experiments that show proof of principle demonstration of this type of recovery. And what we have proposed is that the Dicke model is in fact scrambling enough that we can use it to recover information that is scrambling by just tracing. I mean, the idea is that if you have a qubit and then you put it in a black hole and you scramble the information, you look at the Hawking radiation only a little bit part and you lose a lot of information. Then by doing the dynamics, if you post select, you can reconstruct the qubit. This is super fast. I just wanted to measure that we have been able to show that in fact the model is scrambling enough that can in fact behave as a scramble as necessary for recovery from as it has been postulated in black hole. With that, I'm running out of time, so let me thank you for your attention, and hopefully I convince you that the Dicke module is very rich and necessary.
Thank you very much for this nice and forward-looking talk. We have time for 2 questions.
One thing in your phase diagram or the chaos diagram, will the equilibrium transitions, I mean, are we in the normal phase or superradiant phase of the Dicke model, or does it matter, or does it coincide?
Yes, so I think when you are talking of, yes, so these are dynamical transitions. So the equilibrium transitions are not chaotic, but there are, it has been shown that the model that actually there is some excited state transition that could have, so if you look at the spectrum of the Dicke model, while the ground state is not chaotic, you look at the statistics of the eigenvalues of the Dicke model. In fact, for certain parameter regime, is determined. So there are, I mean, the chaos comes from the excited state, and this is what is reflected in this type of quantity. It's not. It's really trying to explore. I mean, we explored, I didn't bring it, but we did explore the Ryan to normal transition before, but it's just normal. I mean, in cavities, something also.
Right. So you mentioned sometime in the middle of your talk that you went to a chaotic regime with your trapped ions. Now, whenever I've tried to study trapped ions in a chaotic regime, I've immediately ejected the ions. Okay, so do you see such in the experiment? What is the manifestation of? I mean, my studies are confined to Paul trapping, but of course, there's a pinning trap. So you have a spin, but the point is that is coupling to your motional degree of freedom.
Yeah.
So once you go into the motional degree of freedom, what is actually, do you lose ions?
No, we
No?
don't use ions. I mean, the phonons here, we cannot measure, or we have not measured the phonons directly. In the theory, we see that the phonons start to become highly populated. And we are only exploring the center of mass mode.
Right.
So I think in some sense you are creating, and you can see the exponential product, the exponential growth. I don't know. There can be some fast generation of phonons, but that doesn't manifest in any of the, we don't see any, the theory and the experiment agrees perfectly. The only thing that we need to account for is light scatter.
So you can sit indefinitely in the chaotic regime, or it's
No, not indefinitely. You can see this is the chaotic regime, and you can see the expectation value of this, dams at some point, but it's what is expected from the theory because the spins and the phonons start to become highly entangled, and when you measure an observable of the spin, then it damps very fast, and you can see that there are erratic trajectories on the magnetization. These are experimental data that agree with the theory, but that's what we see. We don't see anything. We are only populated the center of mass. I don't know if because in the pinning trap, the center of mass is a little bit more stable than in full trap. I don't know because we have many ions, so we have like 80. So I don't know. Maybe this could be interesting on what is the stability of the phonons.
In the interest of time, and because we have 3 more chances to ask any questions, including later this afternoon, we want to thank all the speakers from this morning's session.